This lesson will describe how to predict the products of double replacement reactions. First, identify the charges of each ion of the aqueous reactants available. Silver nitrate, made of the two ions silver and nitrate, has the following ions and charges. Potassium phosphate, made of the ions potassium and phosphate, have the following symbols and charges. This lesson assumes you can write the formula for an ionic compound given the symbols and charges of ions. Let us start with silver nitrate. The charge of 1 positive for silver and 1 negative for nitrate creates a compound with 1 of each ion present. Since the charge of potassium is 1 positive and the charge of phosphate is 3 negative, the ratio is not 1 to 1. This would require 3 potassium but only 1 phosphate ion. Double replacement reactions require 2 aqueous reactants. Therefore, the symbols AQ will be written alongside of each of the reactants. Let us now switch the positions of the cations or positive ions, which is what occurs in double replacement reactions. The correct charges for each ion must also come with the ions as they trade places. This creates 2 new compounds with the following formulas. Potassium nitrate, silver phosphate. In order for a double replacement reaction to occur, one of these 2 products, either silver nitrate or potassium phosphate, must be insoluble in water. Let us consult the solubility rules to find out if this holds true for either of these. Notice that the solubility table is divided into 2 parts. The left side describing soluble compounds and the right side describing insoluble compounds. We're looking to identify the insoluble compound that would have formed from double replacement. Since nitrate ion was present, the compound formed from the combination of nitrate with any other ion would always form a soluble compound. Therefore, that compound would remain aqueous. However, phosphate ions are typically insoluble unless it's combined with a group 1A ion or ammonium. In this case, our phosphate ion is the insoluble compound. Therefore, we will mark these compounds accordingly. One will remain soluble in water, given the symbols AQ, the other insoluble water, given the symbol S for solid. Since the phosphate ion is insoluble in water, we give that the symbols of S for solid, and the nitrate ion remains aqueous. We give that the symbols of AQ. If by chance both new compounds that form remain aqueous or soluble in water, this would be an example where no reaction happens. For example 1, because silver phosphate is insoluble in water, a double replacement reaction occurs, and we mark silver phosphate accordingly with the symbol S for solid, meaning insoluble in water. Let us look at example 2. Remember to first identify the ions present that participate as reactants. Next, write the formulas for the reactants using the charges of the ions. Once you've written the formulas for the reactants of the compounds, switch the positive ions to write formulas for the products possible. Now we write the formulas of the two new products. Next, we consult the solubility chart to see which of the products does not dissolve in water or is insoluble. In looking at the chart, we see that we have chlorate ions, which we are interested in as products, and we also have carbonate ions. All chlorate ions are soluble in water, therefore the chlorate compound dissolves in water. The carbonate compound, however, remains insoluble in water because it is not combined with a group 1A ion nor ammonium ion. Therefore, we will mark those compounds accordingly. Since the chlorate ion remains soluble in water, we will give that the symbols of AQ, and the carbonate will get the symbols of S for solid, meaning insoluble in water. We have predicted the products of this double replacement reaction. Again, keep in mind, if both of the products created compounds, were compounds that were aqueous or dissolved in water, no double replacement reaction would occur. Let's now look at the third example. This third example is a little bit of a special case. The symbols for one of the reactants are already provided. Since it is an acid, you can see H2SO4 represents sulfuric acid. H2SO4, however, is made up of two ions. The hydrogen ion with a charge of 1+, and the sulfate ion with a charge of 2-. Hence the formula H2SO4. Calcium hydroxide is made up of the ions calcium with a 2+ charge, hydroxide with a 1- charge. This is that special form of double replacement reaction, sometimes known as neutralization. Let us first write the symbols for the reactants that form. Now we will have the ions trade places. The hydrogen ion and calcium ions will replace each other. You can see that one of the products will be water when the H and OH ions collide or come together. Hence, the special type of double replacement known as neutralization occurs. When the calcium and sulfate ions collide, they make the compound known as calcium sulfate with the following symbols. Consulting the solubility chart for calcium sulfate, we would see that this remains aqueous. Water, as you know, is typically liquid. Let us look at one example where two reactants would be mixed where no reaction would occur. If one consults the solubility chart before beginning, one can see quickly that no reaction should occur for the following reactants: copper 2 nitrate and iron 3 chlorate. The products possible for this would become iron 3 nitrate and copper 2 chlorate as the ion switch. However, when consulting the ion solubility rules, we can see that chlorate and nitrate compounds aren't always soluble in water. Let us take a quick look. Here is our chlorate ion. No exceptions are listed. Therefore, all chlorate compounds possible should be soluble in water. The same holds true for nitrate. Therefore, double replacement reaction would not occur here. Any compounds that would form would remain aqueous. Therefore, we write no reaction in a case like this. If we write the symbols for the reactants and then no reaction following, this clearly communicates what we just mentioned. The following reaction in red indicates what we just described. Iron 3 nitrate and copper 2 chlorate products would not be of any significance in this case, since any such compounds would remain aqueous in water. If the compounds began aqueous and would turn into compounds that remain aqueous, no chemical reaction or double replacement reaction occurs.